Let's do a shorthand for the cell notation. So instead of drawing this giant setup every single time, we can write a shorthand notation for this. So the shorthand notation looks like this. I would write the solid metal, so the electrode, and then a single line, and then everything that's in the solution, which in this case is just M plus aqueous. And on the left, the first thing that's listed, it's always the anode, and then two lines that represent the salt bridge. The solution and the electrode for the cathode go on the right side. So the single line shows a phase separation between the electrode and the solution. The double line represents the salt bridge and shows a separation between the anode and the cathode. The anode always goes on the left, the cathode always goes on the right, but within that section, I think it's convention to write the electrodes on the outside, but it's not a rule. So it would be equally correct if you wrote the solution first and then the electrode, as long as it's for the anode on the left side. If you have multiple things that are in the solution that you need to list, you just put commas in between them. So the single line will separate the solid from the liquid, aqueous, and gaseous components, and you would list all of those in the solution section. So it's redox. What's happening at the anode? At the anode, you have oxidation. So the metal turning into metal plus and an electron, or however many electrons it really needs. And at the cathode, you have reduction. So the metal plus getting an electron and turning into the solid metal. I think the easiest way to remember these is that anode and oxidation both start with vowels. Cathode and reduction both start with consonants. And when I add these together, I have the metal reacting with the metal cation on the other side to make a metal cation and solid metal on the other side. They don't touch each other. It's just the wire connecting the electrodes and moving the electrons so that these redox reactions can happen. Okay, let's take a redox reaction and write a shorthand cell notation for it. So zinc reacting with copper 2 plus to make zinc 2 plus and copper solid. The oxidation half reaction is solid zinc turning into zinc 2 plus. When it does this, it kicks out 2 electrons. And so this is going to be the reaction happening at the anode, which means at the cathode, I have copper 2 plus picking up 2 electrons to be copper solid. So my shorthand, the anode is on the left. My electrode for the anode is the solid zinc. And in solution, I have zinc 2 plus. Separate the two sides with the 2 lines for a salt bridge. And in the cathode, I have copper 2 plus in my solution, and my electrode is a solid piece of copper. All right, let's do a longer example so that you can see what to do when we have multiple things. So example 2, 5 iron solid plus 2 permanganate plus 16H plus, turning into 5 iron 2 plus, 2 Mn2 plus, and 8 H2O. So the oxidation half reaction is 5 iron, just pulling this out of the reaction as written, 5 solid iron turning into 5 iron 2 plus plus 10 electrons. So, okay, it had to be multiplied by 5 to get it up to the correct number of electrons in order to cancel out when these were added together. But really, in the shorthand notation, we don't need the coefficients. So we're just worried about solid iron turning into iron 2 plus and the 2 electrons, making sure that it is, in fact, oxidation. Everything that's left is the reduction half reaction. So 2 MnO4 minus plus 10 electrons plus 16H plus, turning into 2 Mn2 plus plus 8 H2O. So my anode, my oxidation, The electrode is solid iron. The solution has iron 2 plus. That's it. Salt bridge, on the right side, I've got permanganate, and I'm going to put aqueous after this, and then a comma because I still have other things in solution. And H plus is one of those things, aqueous. And Mn2 plus is also there, also aqueous. Now, I don't have to list those 8 waters because I have aqueous as a state for all of these things. What I don't have is an electrode, right? Everything is in solution. Now, this is a full reduction reaction, but there is no solid metal in that part of the reaction that could act as an electrode. But that's fine. Right? The electrode is just there to gather and carry and present electrons for whichever side of the reaction it happens to be on. So you can just add an inert metal electrode for that solid surface. So you must add a solid electrode of some type if you don't have one naturally. The things that work, you could use solid platinum, solid palladium. What you'll do in lab is you'll use a graphite rod, which graphite is just carbon, but the way that it's connected, so the way that the carbon atoms are bonded to each other, allows it to move electrons and transfer electrons very nicely. So you will need to add an electrode for any that do not exist.